we can get started. Okay, shall we begin? Okay, I think I did not check the Zoom. So people in the Zoom, you can hear me, right? It's all fine. Okay. Okay, so let's get started. Maybe I'll start with usual set of reminders. Okay, so there are recorders, like microphones in the classroom. So any noise that you're making is amplified to people in the Zoom. So please try to not make noise in between, during the lectures, and please leave one seat in between when you are sitting. So I think I repeat this every week now, and also please don't use this first row. We have enough seats like for everyone, even if we maintain the distancing. So, because a lot of people join remotely via Zoom. So again, another gentle reminder, like if you're feeling sick or feel like you have headache or like feverish, like whatever it is, like you can stay home and join remotely. So the remote experience is, I think, getting better and better. Like, so now we have seamless integration. We don't struggle. And I am adapting myself to the recorder as well. Like, so if I swap things too fast, it stops recording. So like I'm doing everything slow, like, so it's all fine. So you can ask your friends who are joining remotely about the experience, like it's so far good. So that's always an option. Like if you are feeling sick or if you think you are feeling sick, okay, so it's better to be safe. And there were a couple, well, assignment 1 is due next week. So you have all done a mock submission with A0, right? So there is no excuse if you don't tag your questions, okay? So every question must be tagged in your grade scope. If you don't tag your answer, you get a 0 for the question. Even if you apply for a regrade, the mark is still going to be 0. So there's no excuse for not tagging because you had a mock exam, like mock submission, right? So be careful. Don't try to do this in the very last minute, okay? So try to submit at least a day before the deadline. So deadline doesn't mean you have to submit it at 10 p.m. Okay, so it just means it's the final deadline. Like aim to submit at least a day before the deadline, so that there is no rush. Okay. And regarding late submissions, I think you can submit automatically late. Gradescope is not going to stop you from submitting, but even if it is 1 minute late, you get 5% reduction. So again, no excuses. So don't do it in the last minute. Okay. So I'm repeating these things again and again because the class of 100+ students, we don't want to receive 20 emails asking, okay, I submitted 2 minutes late. Like, can you please accept? Okay. And there is also a question of when is the end term going to be? Like a lot of you ask that question either through email or Piazza or in person. I don't decide the end term date. Okay, so Poly decides it. So I think they are starting to do the timetable now. Like, so probably in few weeks, we will get to know what date is assigned for this course, okay? And as I mentioned before, but I think most of you ask mainly because of your travel plans. At least for my courses, ML and RL, like, so the classes, like the exams are online. So even if you are traveling, like you could take it from wherever you are. So it's going to be online, but you'll be submitting your answers in Gradescope. Okay, so I don't know about the dates, but once I get to know the dates, I will let you know. But I guess you all will know the dates. Like Poly will announce it either in the calendar or through your email. Okay. Okay, so let us get started. So this is one of these lectures where I finished in the middle last week. So how many of you did a quick recap before coming to the class? I know I do the recap in the beginning, but I'm curious, how many of you did a recap yourself before coming to the class? Just 2? Okay. Okay.
Would you please explain a little bit about the report? the report like next to the assignment, the code.
Oh, okay, maybe that's a good question. So, okay, so I think for several of you, this might be the first course where you are asked to write a report instead of just submitting your code. Okay, if that is the case, like this might be useful for you. So basically, the report is summarizing whatever experiments you have done, right? Like so, for every question, like let's say the question asks you to visualize the plot. The plot might be in your Jupyter notebook. Well, of course, it is going to be in the Jupyter notebook, but it also has to be in the report. Okay, you should not ask TAs to refer answers in the notebook for any of the questions. By default, TAs are evaluating your report, and there might be another TA. Like so, the work is distributed. Okay, so there's going to be one TA who is going to check your notebooks, but there's going to be another TA, like or maybe bunch of TAs who are going to distributedly check your report. Okay, so the TA who is checking your report will not open your code. So don't, like, the common mistake that people do is, like, if we ask to visualize the plot, people just say, oh, it is in the notebook. Don't do that. So report has to be complete by itself. Like whatever question is there, you give the numbers, you report the performance, you report the figures, you write your analysis, everything in the report. Okay, so report has to be complete and self-contained by itself, and the code is there to support your arguments and for us to verify that whatever you're saying is true by running it. Okay, so like don't mix both. Does that answer your question?
Yes, just I wanted to know, have a balance between comments on the code and on the report. Should I like avoid commenting on the code?
What kind of comments?
Like every steps I can.
Oh, no, you don't need, okay. You don't need to explain every line of your code by comments, okay? So add comments wherever you think the steps are non-trivial. So, well, in general, like the code should be self-explanatory, right? That's a good practice for writing code. So don't comment for every 2 lines. Right? So like just add comments about the function, like if there's any non-trivial logic that you're doing and so on. Okay, yeah?
I have a question about the real-life data that we have.
Yeah.
When you mentioned that you should do full cross-validation.
Yeah.
So we do it just to make the splitting data to training and validation more accurately and efficiently. And when we find the best hyperparameter for the model, and we want to just to find the regression model, so we should go to entire training without any splitting data after we find the hyperparameter, I mean.
Well, that's a good question. So if you're doing 5-fold cross-validation, like in this example, right? So you will try various hyperparameters with all the 5 folds, and then you find the best hyperparameter. And once you have the best hyperparameter, you have to run your algorithm again with this best parameter and the entire folds, like so. So that gives you the final model. Okay. So there is another question in the chat. Okay, important question. Do we have to write the code in the report? Please, no. Okay, so that is why we are separating code and report. Like so. Well, this is also something people have done in the past. Don't put all your code, all your print statements into the report. Okay, so that is why we have the notebook. So you should execute the notebook once, so that like all the results are there, and then you submit the notebook. Okay, and whenever TAs want to run this notebook, they're going to run it and double check. Okay, well, I should not repeat this warning again and again, but I want to tell this that please don't plagiarize. Like so, if you are copying codes, if you're copying scripts, if you're copying content in the report, we can easily find it. Okay, so the way in which we are evaluating, like one TA is going to check one part for all the students. Like so, he or she will find if you're cheating. Like we have found this several times in the last year. I hope to not see such cases at all this year. Okay, so if we find that you're cheating, you get a default 0 for the assignment. So please don't cheat. Okay, so I think we did a lot of announcements and discussions. So let's get started. Well, like I'm not sure how many of you did a quick recap. So let's do a very quick recap of what we did last week. and then continue. Okay, so I'm not going to talk about the first part of the last week, like where we looked at statistical decision theory. Well, we started with gradient descent as an algorithm. Like we looked at full batch gradient descent, stochastic gradient descent, and mini batch gradient descent, right? Like so, and then we also talked about regularization. Like, so we talked about the geometric interpretation of L2 regularization and L1 regularization, and how L1 regularization gives us sparse models and so on, right? Like so, that was the first part. The second part we did statistical decision theory, like where for both regression and classification, like we wanted to know what is the most optimal function one can get, right? Now, in the case of regression, right, the optimal function was basically expected value of y given x. The conditional mean was the best possible prediction one can make. But of course, to do this prediction, you need access to the true distribution. You don't have the true distribution, right? Like so we discussed how different algorithms are trying to approximate this, right? And then we also looked at classification. In the case of classification, if you remember, like the best possible classifier one can design is basically R max over C, probability of C given X, right? So whichever class which has the highest conditional probability, C given X, that is the optimal classifier. Again, to compute this true probability, you need access to the true joint distribution of C comma X. If you have access to the joint distribution, then what you have is the base like the base error rate classifier, right? Like classifier which achieves optimal error rate, which is the base error rate, right? Like, and so that was the decision theory, and then we looked at empirical risk minimization. Right? Now, let's consider linear regression as an example. Okay, a linear models, like where I have like a bunch of W's, right? Like so, if I have like a, let's say a simple linear model, which is just W0 plus W1x, right? Like which can only fit a line, right? So now, every possible configuration of W0 and W1, you get different classifier, right? So we are going to call each of those possible W0, W1 configuration as hypothesis, right? Now, we also discussed that, let's say this is all possible hypotheses in the world, then the fact that I have a model, which means it limits the number of hypotheses that I can test, right? Like, so for example, this model cannot include W0 plus W1x plus W2x squared, right? So that is out of scope for this particular model, right? Like, so this is a limited model in the sense it can only model lines. And that means that if this is all possible hypotheses, then my model is going to support only a small set of hypotheses, right? Now, I'm interested in finding the optimal hypothesis for this particular problem, right? So now to do that, what we should ideally minimize is the expected prediction error. So the expected prediction error of a hypothesis is given by expected value of the loss, right? So this is nothing but double integral L of y comma h of x, p of x comma y, dx dy, right? Now, we said this is the expected prediction error, or in other words, this is the risk that you're taking by choosing this hypothesis h, right? So we're going to call this as risk of h. Now, the true function, like the most optimal function one can obtain for the problem in hand is nothing but R min of this risk, right? So out of all possible h in the world, so this is all possible h, okay? And this is just h corresponding to my model. Okay, so out of all possible H in the world, whatever hypothesis gives me the least expected prediction error or the least risk, that is my optimal function H star. Okay, now in reality, like for all of our practical problems, we can never achieve this H star. H star is a theoretical quantity, right? Like, so we don't, first of all, we don't have like a model which is going to support all possible hypotheses, okay? And we don't have access to the true distribution. So anyway, there's no point about computing this expected value, right? So this is where empirical risk minimization comes into picture, right? Like, so we discussed that, okay, we cannot minimize the error with respect to the entire distribution, but what we can actually do is to minimize this error with respect to the training data that we have, right? So now, so that is what is the empirical risk. So the empirical risk is given by just the training loss, which is 1 over n, summation over I is equal to 1 to capital N, L of yi, H of xi. Right? Now, if I minimize this empirical risk, which is actually possible, right? Like, so we have the data in our hand, we're just minimizing, it's an optimization problem. So once you minimize, you're going to get a H, we are going to call that as H hat. So this H hat is nothing but R min of R empirical, okay, where H belongs to actually just H model, okay. Now, so this is what we want to do, but empirical risk minimization says that we can only do this. Okay. Now, there are several observations here. Like, so first of all, the true H star that I'm looking for, right? So what if my H star is here? Okay. Now, it might be the case that like I have a problem where H star is outside the support of my model. A good example is like this, the sine function that we had, right? So we were trying to model sine function. If you are doing that with linear regression, like W0 plus W1x, I can give you how much ever data I want to. You will never find that sine function, right? Like, because there's no way that a line fitting model can model a sine function. So in that case, H star was outside H model, right? So it can be outside H model, okay? Now, there is also another issue, like, which is basically, even if the H star, okay, let me just erase this. So for example, right, so even if the H star is inside, okay, now my empirical risk minimization has no guarantee to find this H star. So my ERM solution could be something like this, right? So probably if it's too small font, let me copy this to the next page. Oh, no. Copies. Okay, no, I should not move. Okay, I'm going to zoom this so that. Okay. Now let me repeat probably. So the first case is when H star is outside your model, in which case you will never find the good solution. Okay. So this is where your expertise comes into picture. Like, so you should try to have a guess of like whether this model is going to be supporting what this problem needs, right? Like, so now, even if this H star is inside, ERM has no guarantee to find this because you are just minimizing the training loss. So what is the guarantee that this minimization of training loss is going to give you the best possible generalization that you are looking for, right? So which means that even if H star is inside, often your model will only find H hat, which is something different from H star, okay? So how are you reducing this gap between H star and H gap, like H hat? So that is what makes a difference between a good model and a bad model, okay? Is that clear? Yeah?
Can you repeat? Like what?
Okay, so
The last one.
the last point is even if the true hypothesis H star is supported by your model, ERM has no guarantee to find it because you are just trying to minimize the training loss. You are not minimizing the true objective function, which is the expected prediction error. Okay. Now, depending on like how good is your model, it is going to find a solution which is closer to the H star or not.
In the theoretical
Yes.
value that we should attain, but it's not actually possible since we're using real life data.
Yes.
Okay.
Okay. Okay. So then we started with bias variance decomposition, right? I am not going to repeat that derivation. Okay, so we're going to directly write it. So if you have not revised, probably you should go back and revise it. Okay, so if you remember, like we have some loss function. In this, let's just take the squared error function as an example. So L of y comma h of x is given by h of x minus y the whole square, right? Now, we wanted to understand like what are the various components that causes the error, right? So we took one step towards this understanding in the previous lecture. Okay, so I'm going to directly write like what we came up with. So the expected loss is given by expected value of h of x minus y the whole square. Okay, and we kind of decomposed this into two components. Okay, I don't want the equation, but can somebody remind us like what were the two components? Okay, maybe next year I should add an in-class quiz component.
Why an export?
Sorry?
Why an export? Why given x and x?
Oh no, I'm not asking for the equation. So
Can you use the variance?
Sorry?
The variance formulation?
Yes, variance of what?
Variance of this equation hx minus y minus the expectation of the hx minus y.
Okay, well, maybe let me first write the equation. So we split this into two components. Okay, so well, I can rederive it. It's going to take us 15 minutes, so I don't want to do that. So the first component was something like this, right? And the second component was the variance of y given x. Now, even if you don't remember the derivation, okay, so let's just consider the intuition here. So we have a model which makes some mistakes. There is a loss that you are incurring, okay? Now, what are the different sources for the loss, okay? At least at this stage, we have identified two sources. So the first source that you are seeing is basically about the imperfection of your model, okay? Because we know that the true function that is going to have least error is E of y given x, right? Now I have some model h of x. Now this h of x is not a perfect model, which means it's going to make some mistakes, right? So the mistake of the model is captured by this term. So, and then we have a second term in the loss, which is just the variance of y given x, right? Now, you can realize here that this variance of y given x has nothing to do with the model. It comes from the data distribution. So I have some x and y, and the distribution itself is noisy. It could be because of the measurement error, as somebody mentioned last week, or it could just be because of the reason that the process itself is stochastic. Okay. Now, the problem has this inherent noise, which is captured by the second term. Now, first thing that we should accept is the fact that we can never reduce this error. Okay, so this means that whatever you do, you cannot achieve zero error, like for a problem, if the problem itself has some variance. Okay, so what we can aim for is to minimize this error. Now this error is going to be 0 only when we have h of x is equal to e of y given x, right? And we also know that we can never achieve e of y given x. So which means we can do our best to minimize this first term. Is that clear? So I think that is where we stopped, right? Now, in the first part of this lecture, let's try to take just this term, okay, which is the loss due to the model, and see how can we decompose this even further so that we can attack it individually and get better performance, okay? Now, let's consider h of x minus e of y given x, the whole square, okay? Now, in practice, we always work with a data set, right? So we have a data set, let's say D, okay, which contains only a finite number of n data points, right? So whenever I say h of x, that hypothesis is conditioned on the data set, right? Like if I change the data set, I'm going to get a different h of x. So hereafter, we are going to call this as h of x given the data set, okay? So what we have here is h of x given the data set minus e of y given x the whole square. Is it fine? So this is the term that we currently have. Now we are going to take expectation with respect to the data set, okay? So we could have any data set, right? Like so now I can sample a new data set for you and give it to you. Okay, now your model will have different laws. I'll sample another data set and give it to you. Your model is going to have different laws. Okay. Now, then the question is, on an average, what would be your model's performance if I give you different data sets, right? Like so, then that is basically expected h of x given d minus e of y given x the whole square. Okay. Now, I'm going to do the same kind of derivation like last time, okay? So if you remember last time, we added plus e of y given x minus e of y given x, right? Like so similarly, I'm going to do h of x given d minus expectation over the data h of x given d. So this is basically the mean of h, okay? Plus expected data h of x given d minus e of y given x the whole square. Okay, so all I have done is added and subtracted the mean of the first term. Okay, so this is same as the previous equation. Okay, so now you can see we are going to do the same tricks. Like so, I'm going to consider this as a, I'm going to consider this as b. Okay, so you're going to do a plus b the whole square. So this becomes expected value of a square, okay? So h of x given d minus expected value of this, the whole square, okay? Plus b square, so it's e of d, h of x given d minus e of y given x, the whole square. Is that right? Yeah. Okay, I think. Okay, plus 2ab, right? So 2 times a multiplied by b. Okay, so all I have done is like just did a plus b the whole square. Okay, now just like last week, this particular term, right, you just expand it, cancel things, you're going to get 0. Okay, so this is equal to 0. I'm not going to do that same set of steps like last week again. So this is an exercise. You can expand it like it's just a boring logic, and then you're going to get 0. Okay, so we just need to care about the first 2 terms. Okay, so let me take the first 2 terms to the next page. Okay. Now, okay, so I think I missed something. Okay, maybe it's just easier if I rewrite this. So here you have expected value of h of x given d minus e of y given x, the whole square. Okay, so this is the second term, plus the first term is e of d of h of x given d minus ed of h of x given d, the whole square. Okay, so I think this is good enough. Let's just keep this. Okay, so now what have I done so far? So I took the model's error, I split it into 2 parts. Okay, now we'll probably spend like 5 to 10 minutes to understand these 2 parts because this is very, very important. So we are going to name the first part as the bias, error due to the bias of the model, and the second part as error due to the variance. Okay, now let's try to understand what each thing means. Okay, now we know that e of y given x is my best possible model, right? Instead, I'm dealing with a model which is h of x given d. Okay, now the first term, expected value of h of x given d, is what the average performance of this model over infinite number of data sets. Okay, you can try any data set that you want, you compute the average, so that is what the average performance is. Okay, now the gap between these two identifies the bias of the model. So this model has some bias. For example, let's take the linear model, right? Like, so when you have W0 plus W1x, so it has the bias that it can just fit a line, right? But because of that bias, you can try whatever data set you want. You're going to incur some loss. So that is the loss due to the bias. Okay. Now, in the right side, you have the loss due to the variance of the model. Okay. Let's try to understand what is there in the right side. So you have h of x given d, which is basically the error due to one data set, in one data set, okay? And it is subtracted with the average such error. And you have the expected value of that, right? Like, so now this is basically the definition of variance, right? So now in this case, you have like basically like, this is the average performance of your model. This is just one data set performance. So now depending on which data set you are going to use, this loss is going to change, right? So that is the error due to the variance, okay? So maybe let me write them down. So the first is the bias, okay, which is basically extent to which the average prediction over all data sets vary around the average. Okay. Now this is the extent to which the average prediction over all data sets is still different from the true average. Okay. So this is bias. Okay. In this case, bias is squared. Okay. Now we also have variance, which is basically the extent to which solution for individual data set vary around their average. Okay, so now I think we can summarize our discussion. So in general, the expected loss of a model can be divided into 3 different components. Okay, so you have bias square plus variance plus noise. Okay, maybe let me also write the equation for all the 3. So we have bias square, which is basically integral expected h of x given d minus e of y given x whole square p of x dx, right? And then we have the variance term, which is basically integral expected h of x given d minus expected h of x given d whole square p of x dx. Okay, and finally we also have the noise, which is integral e of y given x minus y the whole square p of x comma y dx dy. Right? Now, we know that we cannot reduce this noise. So that's the inherent noise in the system. But we can actually reduce both the bias and variance of the model. Okay, so you can pick a less biased model, which means you're going to reduce this component. Okay. Now, to reduce the variance, you can just increase the size of the data set. Fine. So we're going to talk about the relationship between these two, but for now, is this clear? Yeah, question?
Yes. Why do you put for bias square? Why do you put px dx? For variance, you just pick the expectation and put px dx. That's the definition of the expectation. But for bias too, it's just expectation of the.
Oh, so bias is also an expected term, right? So it's expected, like, if I go back.
Here we don't have expectation.
Okay. Maybe I missed something. I will check that. I will check that and get back. Thank you. Okay, is it clear? Okay. So far, if you got lost in math, okay, so we are going to do a cartoon summary of everything that we have discussed so far. Okay, so this is to catch up so that we can move to the next topic. Now, let's consider this to be all possible hypotheses in the world. Okay, is that clear? Now, when you choose a model, this model is going to support only specific subset of hypotheses, right? So let us just call this to be what the model can support. Okay. Now, for example, let us assume that this is the source for the problem. Okay, so my problem comes from a particular hypothesis H star, okay, and this is the source. Okay, now, as we first mentioned, you can never touch the source because there is already some inherent noise, right? So even if you find E of y given x, that is going to be a little bit away from the source, right? Like, so now let's say this is my E of y given x. Okay. Now this gap, right, is due to the noise. Okay. Now we have a hypothesis. Like we have a model which supports a bunch of hypotheses, right? Now let's say this is the average performance of my model. So this is E d of h of x given d. So this is the average performance of my model. Okay. Now, as you can see, the average performance of the model doesn't match the true function. So there is another gap here in performance. So this gap is due to the bias. Okay, is it clear? Now, what makes this even worse is this is an average performance over all possible data sets. In reality, you have access to only one type of one instantiation of the data set, right? Like, so it could be this data set. So for each data set, you get some value. It could be this, or 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 it could be this. Depending on which data set you are using, you're going to get a specific, let's say E of X, sorry, H of X given D, right? Now there is a gap in performance here. So this gap is due to the variance. Is that clear? So whenever you want to solve a problem, there are three sources of error. The inherent noise, which you can never change. The bias, because you picked a specific model, right? Which you can actually change. So you can play with different models, like which I think you will be doing probably in your second and third assignments. Okay, so we will try different models for the same problem and see what happens. Okay, so you play with different models, you change the bias, you're going to get better performance. And there is a third component, which is the variance. So now, one thing that I want to highlight here is there's always a trade-off between bias and variance. Okay, if you go for a very flexible model, okay, like k nearest neighbor, for example, okay, it is so flexible that there is no model, right? Like, so you just have a bunch of examples and you're averaging. In that case, like, you will have very low bias, but a very high variance. Okay, so when you have flexible models, you're going to have low bias, but high variance. Okay, now on the other extreme, if you go for something like linear model, which is very rigid, okay, so if you go for rigid models, you're going to have very high bias, okay, and low variance. It's highly biased. So bias gives you stability, okay? So like, so when you're highly biased, you have very few options to consider. So the data sets are, you're not going to be that sensitive to the data set, okay? So here is a cartoon explanation of what is happening, okay? So for example, let's say this is the complexity of the model. When I say complexity of the model, well, it's kind of, I haven't defined what is complexity of a model, right? Like, so it could be based on the number of parameters, or it could be based on like what kind of functions, like more and more nonlinear functions and so on, okay? So now, as the complexity of the model increases, my bias will always decrease, okay? So my bias is going to go down as the complexity of my model increases, okay? Now, as the model become more and more complex, it is also going to have variance issues, okay? So my variance, okay, is going to increase. So what we are looking for is something in between, right? So now, if you also plot the true risk, which we can never plot because we don't have access, but if you plot the true risk, okay, so it's going to look something like this. Okay, which means there is actually a sweet spot, right? A sweet spot where you can achieve both minimum bias and variance, okay? And that is what your true function, like that is what the true model that you're looking for. Okay, is that clear? Now, I just want to add a bit about like how to choose models, okay? Now, let's say I have two models, okay? They both have same performance. Let's consider two models, A and B, okay? They both have same performance, but A is a more complex model than B, okay? Now, which model would you pick if you have to pick only one of them to use?
A.
A, why?
Choose the simplest model that
No, I said A is more complex than B.
Oh, sorry, go on.
Which one?
The simplest one.
Okay, so you'll pick a simplest model. Why?
In science, we usually use the simplest model that can explain.
Okay. But can someone tell me why simpler models are better in terms of
The variance
in the words of in the terminologies of machine learning? Yeah.
We have a variance that can be lower and a bias that can be, if we have a lower variance, I guess it's better.
No, when you go for simpler models, you are adding a little bit of bias there. Yeah.
I think it prevents overfitting
It prevents overfitting. Why?
because we have less parameters, less.
Yeah, so simpler models should always have better generalization, right? Like, because when you can explain the data with 10 parameters, then it is better to do that than explaining the same data with 20 parameters, because with lesser number of parameters, you are going to have less chances of overfitting, right? Like, so in that sense, it's better for generalization, you go for simpler model. Okay. Now, this idea of preferring simplest model is like famously called as Occam's razor. Okay, which is attributed to some like really like long back, I don't know which timeline, like maybe 1500 or 1600, like this guy Occam, like, so probably he himself was not aware that this is attributed to him. But the idea is to seek the simplest explanation. Okay, or the other way to put Occam's razor is like one should not increase beyond what is necessary the number of entities required to explain anything. Okay, so you should just use whatever the simpler number of entities that you can use to explain something. Like, so like it's always simpler the better. Okay, so in this example, like if A is more complex, then you would just pick B. Is that clear? So any question about the bias variance trade-off? Any question in the chat? Yeah.
When you say two models have the same performance, you mean they have the same bias, right? Because when we say they have the same bias,
Okay,
the same performance,
that's a good question. Okay.
you are experimenting it on the existing data. So when the model
Okay, no, that's a very good question, right? I understand your question, but just give me a second. Okay, so the question is, is it true that when I say two models have same, okay, maybe I'll ask the question to the class. So is it true that when I say two models have same performance, they have same bias? Yes or no? No, why? Yes, or in other words, the true performance, like the actual performance that you are measuring is a combination of bias and variance, right? So this is where you can play with models. Like, so you can have two models with two different biases, but they could achieve same performance because the performance is measured as a combination of bias and variance. Okay, so it is possible to have two models with two different biases to get the same performance. Is that clear?
But when you talk about variance, we already consume all our data that exists. So
you don't consume, well, so
we don't know the variance, in fact, because we have already consumed all our data. So we don't know.
You don't consume all possible data. You only consume the data set given to you, right? But for the problem, there are like many possible X and Y's for the problem. You have only one specific data set. Now, one model might have higher variance than less, like other model, okay? Which means it might require more data. Similarly, one model might be more biased than other model, right? Like, so, like if you consider the trade-off, like you can combine the bias and variance in whatever way to achieve the same performance. So you could go for high bias, low variance model or low bias, high variance model and still achieve the same performance. Okay, any other questions?
Excuse me, I have a question. If you want to compare two models together with each other, like we should consider the ratio of the validation, like validator data and the test data, the actual model data at the same ratio for both models?
Oh yeah, if you want to compare two models, you use the same train valid test split. Okay, so probably we will stop here and take a 10-minute break and resume at 1:45. So one of the goals for today for me is